we have seen a general methodology for two-sided tests for a mean. Therefore, we have assumed under the null hypothesis up to now that we have a mean which is known, and we have considered a simple case where sigma is known and where xi is normally distributed, but we can, in a straightforward way, extend this methodology to the case where sigma is unknown, and after that to the case where we have xi which is not normally distributed. We keep an IID sample in any case. This is what we have done in terms of methodology. Therefore, when we have a sigma which is unknown but xi which is normally distributed, in this case, we replace the quantiles of the normal distribution by the quantiles of the t, the student distribution, with n-1 degrees of freedom. It's without any problem. This is the thing that we change, and we change the sigma which is known is replaced by its estimate, Sn. And in the case of xi which is not normally distributed, sigma is also replaced by Sn, but we have asymptotic test, we name that like this, in opposition to exact test, when xi is normally distributed. We have asymptotic test if xi is not normally distributed, because we use a test statistic which under the null has an asymptotic normal distribution. That means a statistic for which a distribution tends to the distribution of a standard normal random variable. Now this for the summary of what we have seen up to now, and therefore it's really easy up to now to construct what we name a rejection region for two-sided hypothesis test. Therefore, in general way, I could say as a reminder before beginning this video, we have W mu, which is xn bar minus mu naught. Mu naught is assumed under the null hypothesis. Here we have sigma, that is multiplied by the square root of n. Therefore, sigma could be replaced by Sn in case sigma is unknown, and we could have xi which is normally distributed or not. In any case, we say that for a two-sided test, we have a rejection region which is given by the absolute value of mu, which is strictly larger than z index 1 minus alpha divided by 2, the 1 minus alpha divided by 2, the quantile of order 1 minus alpha divided by 2 for the standard normal distribution. In case this xi is normally distributed but sigma is unknown, the quantile z 1 minus alpha divided by 2 should be replaced by the equivalent quantile of the student t distribution. Just a remark with respect to that, when you see the student distribution and the normal distribution, as I said before already, when the number of degrees of freedom of the student distribution increases, the student distribution becomes more and more similar to the normal distribution. That means that at the moment the quantiles of these two distributions, are really similar. As a consequence, often we say that when n is larger than 30, the quantiles of the normal distribution and the quantiles of the student distribution become really similar, and they can be considered as the same in a way. That means that when you have xi which is normally distributed, or when xi is not normally distributed, and you use an asymptotic test in this case, an asymptotic test, typically we use it for n larger than 30. In those cases, you have the same rejection region, because the t and z here are the same. When n is larger than 30, okay, I'm going to write that as a remark here. as a remark, we can say that when n is larger or equal to 30, z 1 minus alpha divided by 2 becomes really similar to t n minus 1 minus alpha divided by 2. We are in this case where the student distribution and the standard normal distributions are really similar. Obviously, this value n 30 is subjective, and this is not really, it could be another value in another course, but we can say here in this case that when n is larger or equal to 30, we can say that the central limit theorem is correct. And when n is larger than 30, therefore that means that we can consider that that asymptotic test based on xi, which is not distributed as a normal distribution, meaning that we can use the central limit theorem. That means we use the quantile z1 minus alpha divided by 2 here. Okay, therefore in this case where we use the central limit theorem for n larger or equal to 30, that means a test which is asymptotic. In this case also what we can say is that the student distribution in this case with n minus 1 degrees of freedom is really similar to the normal distribution. That means that in this case we can exchange the quantile z1 minus alpha divided by 2 by the quantile tn minus 1 minus alpha divided by 2. That means that in this case you can consider when n is larger or equal to 30, the confidence interval, the hypothesis test, but the confidence interval, it's the same. But when n is larger or equal to 30, we can consider that the hypothesis test, the rejection region of the statistical test when xi is supposed to be normal, when xi has a normal distribution, meaning this rejection region constructed with the t distribution, and when sigma is unknown, obviously, is the same rejection region, or more or less exactly the same, more or less the same rejection region as in the case of a case where we consider that xi is not normally distributed, and then in the case where we have to use the central limit theorem. Thus, interesting remark, this is an interesting remark to begin this part here. Okay, either we consider the case of an exact hypothesis test, where xi is normally distributed, we get a rejection region of this form where we have this quantile, when n is larger or equal to 30, or in the case where we consider that xi is not normally distributed, therefore we have to use the central limit theorem, we have an asymptotic test. In this case we have a rejection region which is characterized by this inequality. In both cases we have the same rejection region. We have the same rejection region for either the exact test for the mean or the asymptotic test for the mean. Therefore, either the case where xi is normally distributed or the case where xi is normally distributed. Therefore, in both cases, obviously we consider sigma is unknown, therefore we have to estimate it. But anyway, in both cases, because the student and the normal distribution becomes very similar when n is larger than 30, we can consider that the rejection regions are the same in both cases. We can consider that the rejection regions are the same, almost the same, thanks to the similarity of distributions. Because that is a remark to begin the next part of the hypothesis test. This is true for the other hypothesis test. That means that when the student distribution is very close to the normal distribution, we can consider, we will consider in other situations as well that rejection regions are the same. And that can be applied, therefore, in different contexts in the next test that you are going to see. This reminder gives us here the critical region. Let's say this is a critical region. This is a rejection region, but which is also named critical region. The critical region that we have seen up to now is this region, critical region for a test for a mean of x of the variable that we study. That is for the two-sided case. We are here in the two-sided case. And when we are in the one-sided case, what happens? Now let's go to the one-sided case. And this is the object of this lesson. Let's go to the one-sided case. The one-sided case. This, I remember, in the one-sided case, I'm not able to draw lines. I'm sorry, I'm going to do it better like this. In the one-sided case, what happened? What happens? The one-sided case, we said, okay, we can have under the alternative, we can have something like this, mu equals mu naught under the null, and under the alternative, for example, mu strictly larger than mu naught. This is a one-sided test. On the right, we have seen that before. Thus, here in this case, we have to transform the critical region. We have to transform the critical region of the two-sided test in a critical region for the one-sided test on the right. How did we do previously? We said previously, okay, we were looking at this quantity. And we were saying, okay, in the case of the two-sided test, when this quantity is too large, that means that the null hypothesis becomes unlikely. Too large, but in absolute value. Therefore, xn too large, really smaller than mu naught, or xn really larger than mu naught. In both cases, we have said, okay, the null hypothesis becomes unlikely. In this situation, under the alternative hypothesis, when will we validate, when will we say that we reject the null hypothesis? When mu is strictly larger than mu naught. That means when the observation of xn bar, an estimate of mu, is really larger than mu naught. That means larger than a quantity, not the absolute value larger than c, but the value itself without absolute value, without modulus. That means in this situation, to make calculations easier, to have a statistic test and to be able to make calculations, okay, we introduce the statistic test, the W mu, but here the rejection region or the critical region will be this one. When we have a statistic, an observation of the statistic test which is larger than a threshold, not the modulus, but the value. And here we could write it y mu without modulus, y mu strictly larger than c, strictly larger than the value c. And as we have seen in the case of the two-sided test, a very important characteristic which makes that we have said in the two-sided case that we have a critical region. The critical region in every hypothesis test has a maximum value alpha. This is the definition of the level of significance of a test. The critical region under the null hypothesis has always, and I could write that in red as well, because it's really important, the probability of this critical region, if the null is true, in all the cases we have seen up to now, this is the probability of rejection of the null hypothesis when the null hypothesis is true, this is alpha. That means that up to now, what we have seen is that every critical region, every rejection region has a probability alpha. We do the same here. That means that the probability that mu is strictly larger than c, if the null is true, that means the probability of rejection of the null hypothesis should be equal to alpha, or should be maximum alpha. We are going to see in some minutes why maximum alpha. It's a detail. We are going to explore this detail in some minutes, but okay, let's consider up to now that this is exactly equal alpha, that exactly equals alpha, this probability of rejection of the null hypothesis, probability of critical region, of also probability of type 1 error, if we remember well. This is rejection of the null hypothesis if the null hypothesis is true. This is also the probability of the type 1 error. Therefore, alpha is the test, is the level of the test. But in this case, it's really easy if you compute that. In the case of a normal distribution, if Wn is standard normally distributed, it's really easy to see that here C is in fact Z1 minus alpha. You can compute it by yourself. You will see. You have the probability that W mu is larger than C. This is 1 minus the probability that W mu is smaller or equal to C, and that this probability that W mu is smaller or equal to C should be equal to 1 minus alpha. Therefore, by the definition of a quantile of order 1 minus alpha, C exactly equals Z1 minus alpha. Therefore, it's really easy in this case to compute the critical region for this test, for this one-sided test on the right. In case, obviously, sigma is unknown, but xi is distributed according to a normal distribution. Here we have to put the quantile of the student distribution, and if xi is not normally distributed and sigma is known or unknown, in any case, we can use the central limit theorem, and in this case, we have an asymptotic critical region, and in this case, C is also replaced by Z1 minus alpha. This is thus the critical region for one-sided on the right, W mu strictly larger than Z1 minus alpha. And the probability of this critical region, it is always the same thing. It has value alpha. Thus, we can quickly do the same for a one-sided case, but on the left. Thus, okay, the title of this part is one-sided test. At this video, the general name of this video is one-sided test. We begin with a reminder with the two-sided test, which has been seen very deeply in the previous video. But here we are in the one-sided test, one-sided case, and we have the first case, which is the one-sided test on the right, 1. And we have a point 2. We can immediately write the point 2. One-sided test on the left. What happens in this case? We have mu equals mu naught against h1, mu strictly smaller than mu naught. A critical region. We are going to see now this statistic. When are we going to reject? Obviously, when we have mu which is really smaller than mu naught. When xn bar, the observation of xn bar is really smaller than mu naught. When this quantity is smaller than c. If you make the calculation, if you make computations for all this, this is the critical region, and this is the probability that W mu is smaller than C. In this case, that should be exactly alpha. Thus, what is C? We can clearly rewrite it immediately here. The rejection region, this is W mu, strictly smaller than Z alpha, and Z alpha, this is minus Z1 minus alpha, because of the symmetricity of the normal distribution. The quantile alpha, the quantile of order alpha for a normal distribution, this is minus the quantile 1 minus alpha for the same normal distribution. As a reminder, we have the normal distribution, which is here. You have here Z alpha, you have here 0, you have here Z1 minus alpha, and this Z alpha here, this is minus Z1 minus alpha. This is seen in a basic probability course. This here in this case, we have the rejection region. The rejection region is computed in a very easy way. It corresponds to this. And obviously, if I replace C by Z alpha here, the probability that the normal distribution is smaller than Z alpha, this probability is alpha, and thus we have a rejection region which has probability alpha. Thus, in these two cases, a rejection region seems to be easy to find. Let's see now. Okay, we have, in this case, we have the type 1 error. We have this idea of type 1 error, and we can compute the probability of this type 1 error. This is the level of the test in both cases. But let's see on the graphs, and I would say remark 1, because we have the rejection region. It's already a good thing. With a rejection region, we can say if we reject or not the null hypothesis. We have everything to decide. But what happens for the type 2 error? What happens for the power of the test? We didn't study that. We fully studied that for the two-sided test. Just I would like to show you in the one-sided case on the right what happens with the graphs. What are the differences with the graph that shows, that captures this type 2 error? Let's see that as a remark, I would say, as a remark, because it has been fully explained before. And I would say, okay, remark 1, it is a remark about the type 2 error. And if we talk about the type 2 error, you know that we also talk about the power of the test. And let's see in the case, but similarly we could talk about the case of the one-sided case. We are going to see the one-sided case on the right, but we could similarly compute the one-sided on the left case. Thus, in the one-sided on the right case, here is my reminder about how it works. You remember we have 0 here. Around 0 we have here a distribution, a normal distribution. We can also draw another distribution here, let's say like this, which should be the distribution of the statistic, but when H1 is true, when the alternative is true, therefore for a hypothetical mu1. Here in the one-sided on the right case, we have mu1, we have mu1, the hypothetical mean for mu, which is larger than mu naught. Therefore, we have a graph, a red curve, which lies on the left of the green curve. Would we be in the one-sided on the left case, we would have mu under the alternative which is smaller than mu naught. That means that in this case the red curve would be on this side, would be there. This is not the case here, but it should be the case if we were in the one-sided on the left case. We can draw the type 1 error on this graph, and we can draw the type 2 error as well. Thus, as in the two-sided case, we know that we exactly know if mu equals mu naught, where is the green curve. Let's say if sigma is known. If sigma is unknown, you estimate it, and we know where it is more or less. It is a standard normal in any case. It is a standard normal, or it is a student distribution in case where sigma is estimated, and therefore in this case we have a statistic which is distributed according to a student distribution. Okay, we know where is the green curve. We don't know, because of mu1, where is the red curve. But we can construct here, in the case of the one-sided on the right case, here we can draw z1 minus alpha. In the case of the one-sided on the left case, we would put z alpha here. And in this case, we have the type 1 error, which is here. In the case of one-sided on the left, we would have the type 1 error here. This surface is exactly alpha. And if we want to have the type 2 error, this is this one. This one is beta, and beta also depends on the value of mu1, as in the one-sided and as in the two-sided case. Because this is the type 2 error, this is the type 1 error. Therefore, the probability to not reject, of non-rejection of the null hypothesis when the alternative hypothesis is true. Therefore, here we have a rejection region or critical region. We reject the null hypothesis. And where we do not reject the null hypothesis, in the acceptance region, we can say this is this region. And the power of the test, put it in black, this is this. 1 minus beta of mu1. This is a power which can be computed for a given value of the mean under the alternative hypothesis. And only in this case. We can only, this is a necessary condition to compute this power function. Okay, that's a point. Another remark with respect to that, therefore we can draw that, we can understand that, we can understand how the graphs are moving now in the case of a one-sided test on the right or a one-sided test on the left. It's the same way of thinking. Another thing, another remark about the type 2 error and about the graphs that we have here. Therefore I would say remark 1 here, remark 1, and next remark 2. Remark 2. The null hypothesis in this case could be, let me write that, mu smaller or equal to mu naught. I wrote that in the introduction. For a one-sided on the right case, one-sided on the right case, in the introductory video, I wrote that for the one-sided on the right case. I wrote under the alternative mu strictly larger than mu naught, but under the null, I also wrote the possibility of mu smaller or equal to mu naught, not exactly equal to mu naught. That means that, in fact, under the null hypothesis, we also have, in this case, a mu which is not perfectly known. A mu under the null hypothesis which is not perfectly known, as under the alternative hypothesis. Just a remark in statistics, when all the parameters under a hypothesis are fully known, and allow to fully know the distribution of X, we name this kind of hypothesis simple hypothesis. Therefore, in this case, for example, if sigma, in the previous case, where sigma were exactly known, where we had the value for sigma, and when we had a mu equals mu naught under the null hypothesis, we named that, that's the vocabulary, we named that a simple hypothesis. Most of the case, that's not true, and we don't talk about if it's not the case, if we don't know all the parameters exactly under the null hypothesis, if the parameters under the null hypothesis do not allow to fully know the distribution of X. In this case, we are in a case of a composite. We name a composite hypothesis. That's okay, that's a detail, that's a question of vocabulary, but here typically we are in a composite hypothesis. The value of mu is not known anymore under the null hypothesis. That means that, for example, the green curve, we don't know where it is. We don't know where it is anymore. It could be here. If we take a green, it could be here. For example, right? Could be here. And imagine that this curve is there. It's this dotted distribution that would correspond. You understand? We understand well. Huh? We have a mu which is larger than the true mean. Therefore, in this case, if we compute the distribution of x in bar minus mu naught, you can compute that. We have distribution of the resulting statistics square root of n times x in bar minus mu naught divided by sigma. The distribution should be located somewhere here, and should look like a normal or a student and a thing, but it should be located on the left of the solid green curve, which is here. And in this case, imagine that we are in this case. Therefore, we assume here that we have a hypothetical hypothetical mean, which is true under the null hypothesis, which could be, for example, mu naught prime, another mu. In this case, we would have the distribution of the statistic under the null, which has a type 1 error here, which is really smaller than the type 1 error that we had with the solid curve. But we don't know. We don't know where is this dotted distribution. Where is this dotted? Where is this dotted line? Where is this dotted curve? We don't know it. We can show that it is normal, and we can show. I'm not going to do it here because it's tedious calculations. It's not really important in this case, but we can show that for every curve, for every dotted curve, for every hypothetical mean of x under the null hypothesis, we have a type 1 error which has a probability which is always smaller than the probability of the type 1 error for the solid curve. That means, in this case, the type 1 error, the probability of type 1 error, in this case, is always smaller than the probability of the type 1 error when mu equals mu naught. Therefore, the probability of the type 1 error, that could be the probability of the type 1 error computed with this curve for a mu which is a hypothetical mu under the null hypothesis. And we can see that the probability of the type 1 error, this is the surface here under the dotted curve here. This is clearly, we see it on the graph, it's always smaller than this surface computed under the solid curve. The probability that the statistic is above the threshold, therefore the probability of the rejection region is really smaller with this dotted curve than with this solid curve. We can show it. I'm not going to do it, it's tedious, as I said. There's the probability of type 1 error. In this case, the probability of type 1 error for the dotted line. For any mu, I would say I could write here conditionally on mu equals mu naught prime, but I don't know what is mu naught prime. It's hypothetical mu, which is true under the null. This probability of type 1 error is always smaller or equal to the probability of the type 1 error when mu equals mu naught. That means when we are working with this green curve, with this solid green curve. That means that, okay, we are going in this case to just redefine a bit what is the level of the test. Up to now, we have said that the level of the test, this is always alpha. Here, the level of the test, in this particular case, thus, not going to put that in red, it's not necessary, but the level of the test, here, it is not the probability of type 1 error exactly, but this is the supremum, the maximum. In this case, it's a maximum, but in general, the level of the test corresponds to the supremum, it corresponds to the supremum of the probability of type 1 error, the supremum over all the possible values of the parameters that are assumed under the null hypothesis. This supremum over mu smaller or equal to mu naught in this case. The level of the test is defined as the supremum of the probability of the type 1 error, the supremum over all the possible values that are assumed in the composite hypothesis under the null hypothesis over all the parameters that are under the null hypothesis, that are tested under the null hypothesis. And in this case, this is the supremum over mu smaller or equal to mu naught, over all the mu's that are smaller or equal to mu naught. And in this case, it's really simple because this supremum is exactly the probability which is computed with the solid green curve, which is here. On the other side, we could have the same thing with a one-sided test on the left. In this case, we would have a dotted curve that would be on the right, and the red curve would be on the left. And therefore, we would have also the same thing. We would have the solid green curve there that does not move. And there as well, the type 1 error, in this case would be on this, would be observed on this side. And here again, the level of the test would be alpha, and it would be the type 1 error computed with the solid curve. All the probabilities of type 1 errors computed with dotted curves on this side. The probability of type 1 errors in those cases would be smaller than the probability of the type 1 error computed with this solid curve, and they are always the level of the test would be alpha, but the probability of the type 1 error in reality with the true, if the null hypothesis is true with a mean which is smaller or equal to mu naught, that means for a hypothetical mean mu naught, the probability of the type 1 error in this case is smaller or equal to alpha. Therefore, okay, as a conclusion of this remark, when we assume under the null hypothesis this kind of things, this kind of what we say composite hypothesis, the level of the test is alpha, but the probability of the type 1 error could be smaller or equal to alpha, is smaller or equal to alpha. It can be alpha, but it can also be smaller than alpha. In the two-sided case, we have a level of the test which exactly equals the probability of the type 1 error. That is for this remark 2. And since we are here, we can also draw, and I'm going to conclude this video with that, the power. We have talked about the power, and we have said in the case of a two-sided test, we have seen a power function which is like this. If I can draw it again, I'm not going to draw it again, but I'm going to say, okay, here in this situation, we are exactly at mu naught here. And here we have an axis, which is mu1, we had said, and we have said, okay, the power of the test, the 1 minus beta, the probability to reject when we have to reject, should be very close to 1 when this is 1 minus beta theta of mu. We can write mu here. In the case, we have to distinguish. I'm not going to write mu1 in this case. I'm going to write a general mu as if mu is a variable. For the x-axis corresponds to mu, different values of mu. Here, in this case, obviously, the power should be really small. And we have said that in the case of a two-sided, I'm going just to put dotted here. In the case of this is the shape of a power function. It should, when mu is close to mu naught, the power is small. Power which is close to 1 when the true mu is really different from mu naught, therefore far away from mu naught, we have a power which should tend to 1. This is the function for the two-sided case. Therefore, something which is close to 1 here, and here a power which decreases. That's the shape of the curve. It's not the exact curve. It should be computed for each case. But here, when we are in mu equals mu naught, the probability to reject the null hypothesis in the case of in the simple case where sigma is the same under the null and under the alternative, in the case where mu equals mu naught, we have a power which corresponds to maximum alpha here. For the one-sided, for the two-sided case, in the two-sided case, it's exactly equal alpha, in fact. That can be computed. That it's not really important. What is important is to understand that, okay, the power, therefore, when mu is close to mu naught, the probability to reject when we have to reject becomes small, and it can go down to alpha when mu is very close. When mu becomes mu naught, the probability of rejection in this case, you see that the red curve and the green curve are exactly the same for the two-sided test. Okay, for the one-sided test, what happens, that is what I wanted to draw initially. This is something like this. Let's say here we have alpha. This is something like this. The curve should be something like this. Here is the power. You see, that is the curve this is the power for the one-sided on the right test. Here you see under the alternative we have mu which is larger than mu naught. Because we are here, and when mu is larger than mu naught, the power should be large. The power should be closer and closer to 1. As close as possible to 1. Because we reject, and it's true. We should reject, because H1 is true. Thus we have an increasing of the curve here. But when we are here in values of mu that are smaller than mu naught, in this case, if mu is smaller than mu naught, that means we are not, in fact, under the alternative hypothesis. We are under the null. Thus the probability to reject under the null, this should be seen as the probability to reject for a mu which is smaller than mu naught. Therefore, that should be seen as a probability to reject when we are not under the alternative in this case here. We are under the null for these values of mu. Therefore, this is not exactly the power of as we have defined. This is the probability to reject. This probability to reject, in this case, this probability to reject should be very small, because in the case of the one-sided on the right test, here we should have a probability to reject when it's true, which is small. And we have seen that this probability to reject, in this case, with the way we constructed this test, we have seen that the probability to reject when the null is true, and especially when the null is exactly mu naught, this is exactly the probability of the type 1 error, and this is exactly alpha, the level of the test. Thus here, in this case, if I draw in orange here the probability to reject, when mu equals mu naught, the probability to reject, that means the probability of the rejection region when mu equals mu naught, this is exactly the level of the test, this is exactly the probability of type 1 error, with mu equals mu naught, with mu equals mu naught, this is alpha. And as we have seen, for other values of mu prime, mu naught prime, which is a hypothetical mu which is smaller than mu naught, the probability to reject when mu is smaller than mu naught, therefore when we don't have to reject, therefore this is, the probability to reject when we don't have to reject, this is a type 1 error. In this case, we should have a probability which is smaller than this probability, which is alpha. We should have a probability which is smaller than this probability, which is alpha. Thus we should have something here. You see that, okay, in a way, tends is very small and tends to 0. Because that is the shape of a power function in the case of a one-sided on the right test. And immediately we can transpose it on the case of the one-sided on the left test, and we can imagine that in the case of the one-sided on the left test, we should have something like that. We have really understood that. We understand that very well. This is something like that. And I don't see anything more about that. This is exactly the symmetric of the orange curve. This is the yellow curve that I'm drawing here, something like this. And okay, this closes this video about one-sided test on the right or on the left.